All right, this is lesson 143, working through more astronomy, and I wanted to take just a moment and review a little bit with you. And so in the last lesson we did something similar, but we'll make this a little bit smaller this time. So we've got stars and we have constellations. And so we'll make this quick. I'm going to try. So I'll go through a couple of the first ones. First of all, let's try to change it up. So let's go with Regulus. Okay, and which constellation is going to be associated with that? Of course, you should be thinking Leo, and of course I'm going quick. So Regulus, Leo. Let's do it this way. Ursa Minor. Okay, what constellation is associated with that? You should be saying Polaris. I think I said constellation. What star is associated with that? And so I wanted to go from constellation towards star. Let's try another one. From the first set. Let me get a good one for you here. We had Leo. Oh, here's another one. How about Bootes? Okay, Bootes has Arcturus. And then let's go with Spica. Spica is in what constellation? You should be saying Virgo. Okay, I am going fast on purpose. You need to know these. Another one that you want to know is Deneb. Deneb is in, okay, this is Cygnus, the swan, Altair, okay, that is in Aquila, the eagle, and Vega, probably more important one there. Vega is going to be in Lyra, right? So that was kind of the first lesson. You definitely wanted to know those. Know them back and forth. Of course, these bottom three again make up the summer triangle, Deneb, Altair, and Vega. I definitely want to know those three. All right, then we talked about Sagittarius and Scorpius and all of those. Now I'm going to clean this up and we're going to do the same thing, but this is kind of the second lesson's review. So we had stars, okay, so there's that, and then we had constellations. Okay, constellations. And so we were looking at several of them. All right, let's start with the constellation of Scorpius. Scorpius should stand out to you as the one that has the bright red star in it. That one is Antares. Remember, the rival of Mars or against Mars. That's Antares. Then we also had Sagittarius, of course, the teapot asterism, but not necessarily a bright star that we need to know. Then we talked about Cassiopeia, again, not a major star. Cepheus, also not a major star. Andromeda, the daughter of the two. Andromeda, of course, has, and I'm on 317, I'm just going through the list, the Andromeda Galaxy, which is the closest galaxy to us, also associated with the Great Square and Pegasus. There's another one here that was given, that was Perseus. Perseus is the hero, and so Perseus has Algol, which is the star that's supposed to be the head of Medusa, that you definitely want to know of. Now this is the one that's going to probably be the biggest one of note, and we have Orion. Interestingly enough, you have, and probably better if we draw him, so again, kind of our hourglass shape. Here's our three stars. Draw something like this, get our shape, get him pulled out. Of course, he's got this arm over here, got his shield, and it's not a shield, I'm sorry. It's actually supposed to be a lion's skin. He's got his club up here, and then sometimes some stars up here, kind of like a head. But again, some sword hanging down from the belt. Now this is Orion. At the very top, this top left star is Betelgeuse. Okay, Betelgeuse. At the bottom right, you've got Rigel. And at the top right, you have Bellatrix. Okay? You definitely want to know the three of these incredibly well if you've not already seen it. So all three of these are associated with Orion. After that, you've got Gemini. Gemini, I mentioned before, kind of looks like this, and there's two stars kind of top and both sides. Gemini is known for Castor and Pollux. And then, of course, you've got Sirius, you've got Canis Major. We'll call him Canis M. And so that's Sirius, brightest star in the night sky. This is, of course, the dog, to the left there, Canis Major. And then you've got, after that you had Taurus. Okay, and so Taurus is, of course, Aldebaran, kind of the Baran. Okay, Aldebaran. And so that's kind of the main one. So you definitely want to know these stars, definitely want to know their locations, definitely want to be able to find them on labels if need be. Of course, also Taurus has the Pleiades, the open star cluster. All right, that's what we've learned in the past. I'd like to start on 322 then and talk just for a moment about Centaurus. All right, so that brings us to Centaurus. This is actually something that we can't see here where we stand. We live in the northern hemisphere, so of course here you are standing here, and you kind of have the entire northern sky above you. This is the celestial sphere. All the stuff at the bottom, Centaurus is down here. You can't see it. And so the horizon blocks that off from you. You can't see certain stars, and of course it doesn't ever rise above this, and so you are stuck on this one. But if you ever get a chance to go to the southern hemisphere, you might get to see Centaurus. It's the southern Centaur. We have a northern Centaur, that was Sagittarius, and the southern one would be Centaurus. And so the two front teeth apparently are Alpha Centauri and Beta Centauri. Mentioning those for just a minute. It appears to be one star. Again, you've got Centaurus, and also this important constellation right here, Crux, supposed to be a cross. Still root word in the word crucify, crux, excruciating, all of those have to do with the cross. And so there's Centaurus, kind of a weird looking shape. Let's talk about Crux. It's actually a cross constellation. You'll notice that. Obviously, I went very quickly through Centaurus. Crux will be found on 323. It's the cross constellation. Now, it's between the legs of Centaurus. Circumpolar in the southern hemisphere, so we'll never see it in the north. Forms the asterism of the Southern Cross. Although the southern hemisphere has no pole star, the upright bar of the cross points south. And so, if we have the celestial sphere, you've got your North Pole, South Pole. Up here you have the North Pole star Polaris. Down here you have really no pole star, but you actually have down here Crux, not to be confused with the Northern Cross. That was Cygnus the Swan, which would be up here somewhere. Okay, but this particular one, if you point down this way, you'll find true south using that. And so people in the south will use Crux to find true south. So it's more of a pointer than it is a perfect constellation. So here we go. Looking at a picture of Crux, and you'll even see him here. This is a beautiful picture, but not so much my line skills, but something like this, even something like this. And so there's Crux. Of course, again, Centaurus kind of goes all the way across the top of this. Okay, so there's that. All right, so that's Crux. Again, here's another picture of the Southern Cross asterism, not to be confused with the constellation Crux. All right, page 324, we change our topics completely. When I get back, I need to go through Stellarium, and I'd like to get to a point where we can kind of just go through the sky and find everything using the Big Dipper and Orion. It's really important, but we do have very little time. So we need to start talking about the sun, star, and galaxies. Obviously, the most important star to us is the sun. It's close to us, and we see it every day. And so the most important star to us on Earth is the sun. There are millions, even trillions of stars, but this particular one, even though it looks very big to us, is simply a typical average star in size, temperature, and even shape. And so that's important. It keeps the planets in orbit because of its immense gravitational field. And of course, here would be the reason why at the bottom why we'd study the sun. If we study the sun, we essentially are studying stars. And because so many stars are trillions of miles away or even light years away, closest one, Proxima Centauri, we can't even study them because they're so far away. So we'll study the sun in the meantime. Of course, the big yellow one's the sun, as you know. And so here is the sun in its immensity, its majesty. It's a powerful star. Again, just an average star. But we know that it is used to rule the day and to make sure we know the difference between night and day. Of course, you see some size comparisons between the gas giants there at the bottom, and you even see the sun. See the here's the Earth, little pellet here. Here's your four gas giants. Jupiter. Here's Saturn without rings. Now these ones are a little bit difficult to tell apart. So you've got Uranus, which I'm guessing is this one, Neptune right here. But then you've got the 4 of them. It's, again, these colors are a little off and a little blurry for me, but that's what we're talking about. All right, let's talk about the structure of the sun from the best we know. That picture on 324 is going to be very, very helpful to you. But we're going to look at its components. And so it says, the center of the sun is called the core. The sun is a great glowing mass of gases, mostly hydrogen and helium. In fact, if you do a study of the universe, the best we know, the most common atom in all of the universe is hydrogen. Second most is helium, that being in stars. That are heated to temperatures estimated to be about 6,100 degrees Celsius or 11,000 degrees Fahrenheit near the surface and 27 million at the core. So you'll notice it gets hotter the further in you go. This is very similar to our own planet. Of course, it gets hotter as you go down into the Earth, but maybe not drastically like this. Go ahead and stand on the surface of the sun at 11,000 degrees Fahrenheit. Your oven on a good day is 500 degrees, so we're already talking massive implications here. 27 million degrees, I have no category for that. And so scientists believe hydrogen atoms at the core are constantly fusing to form helium atoms and releasing atomic energy. If you think about nuclear reactors at the basic form are producing nuclear energy by breaking apart and putting together atomic nuclei. Those things we make in labs, the sun does it on in mass all the time, producing that immense amount of energy. Now, that energy is useful, especially to us. If you think about it, there's very few forms of energy that don't come from the sun. I would give you some time to think about it, so immediately you think, okay, well, plants. You can eat those and you feel good and you get energy. Well, no, the sun grows them. Think about wind energy. Well, no, remember wind only blows because of the differences in temperature. Temperature caused by the sun. And so all the energy on our planet essentially comes from the sun. And so that atomic energy is very important. The sun is basically its own nuclear reactor. So here's a cutaway of the sun. We're going to be talking about some of these concepts or these terms as we go, but we're right now focusing on the core. The core is the central of it. Now, let's be clear. No one knows what this looks like. I've not been to the sun. No teacher has been to the sun. Not even stepped foot on the surface of the sun. However, this is our best understanding because of the immense amount of gravity, the density that would have to be there. We would assume it to be solid. All right, let's talk about what's called the photosphere. If you break apart the word photo, it means light, sphere, well, that means a sphere. So looking here, we've got the visible part of the sun. Photo, the one we see. When we view the sun from the Earth, the ball of light we see is only a part of the whole sun. The visible part of the sun is called the photosphere. It is extremely bright, and if you look at it, it will hurt you. The photosphere appears to be covered by bubbles. So photo, light, sphere, sphere of light. The ball of light we see we see the sun as, and that is harmful to our eyes, so don't look at the sun. So when we look at this outer layer, this is the part we see. Of course, there's other stuff going on, but the photosphere is what we see from Earth, and this is the one that gives you the little blue dot in your eye when you look at it. Now, moving on, and again, we don't get to see this beauty and these flaming bubbles because most of the time all we can see is the immense amounts of light energy coming from the sun. But if you could see and you could filter it out, you would notice that the sun is covered by these things called granules. It mentions the photosphere appears to be covered by bubbles, like the surface of boiling water. Basically, the sun itself is like a boiling pot of water. And so you'll notice that these bubbly features, of course there's some cool stuff going on here, but essentially there's this bubbling steam basically that's going on. Obviously it's not water, so it's not steam. If anything, it's plasma. But the surface of the photosphere is covered with these bubbles, and those bubbles are granules. That word means grains. So, over 600 miles across, one bubble is over 600 miles across. So before we look at a picture like this, all right, so one little bubble right here, we're saying that's something larger than the state of Texas that we're looking at. Going back. These are convection cells, and so we're thinking about something like this. When you have your pot on the stove, so you've got your pot, here it is, and it's got a little handle. Of course, there's a flame underneath of it. Of course, the water at the bottom heats up, starts to evaporate, and so you got steam coming out of the pot. As it starts to cool, it starts to fall, and we get what's called a convection cell. Of course, at the top, you'll see little bubbles forming in the water. This is, of course, the evaporating liquid, but those bubbles are actually water molecules that are going up and down in those cycles. And the same is true of the sun. So essentially, the sun is a sphere, but it is covered by these granules or bubbles all the way across, all the way around it. And so the granules are very important. Now, they actually have much larger ones. By the way, each one of those bubbles is going to last about 20 minutes. Much larger convection cells exist on the sun called supergranules. Okay, so magnetic bubbles are called supergranules. And it mentions that those are 22,000 miles across. 600 was pretty big. We're talking 22,000 now. That's a lot. So big bubbles are called supergranules. I've got my pictures a little reversed, but I think you can see what I was going for. Here are the granules going on. Now, again, they're like convection cells that are going around inside of the sun. The bubbles happen because of, we believe, the gases boiling around inside of the sun itself. All right, moving on. Sunspots. Now, no one directly observes the sun. No one takes their telescope, points it at the sun, okay? Points it at the sun, here's the sun, and of course all the beams are coming through, and they look through their eyepiece. Okay, here's the eyepiece. Here's my eye. No one does this. Okay, the best way to do this is actually to take what's called a reflecting telescope. And there's our sun. Take a reflecting telescope, something that's still pointed at the sun. However, reflecting telescopes have an eyepiece that is pointed towards the ground. Now, take your eyepiece out because the sun will actually melt it. This end is actually closed off, and of course, there's a mirror that is right here, so the light comes in and reflects out the tube. And so here's the concrete or something, and you can actually see a projection of the sun that is projected from the mirror. You take the eyepiece out and you'll see it. You can just look on the ground. Now, one thing you'll notice about the sun is it has little dots on it, like it's sick, like it has acne or something. And those particular spots are of great interest to us because if they're on the sun, they might be on other stars. And so they call them sunspots. These are dark patches or freckles on the sun. We're on the bottom left of 325 now. This is caused by the sun's magnetic field, we believe. Most of the planets, even the stars, have magnetic fields. These appear darker because they are cooler than granules that surround them. Of course, that would be why. They range from the size of a granule to 5 times the size of the Earth. And so they simply, interestingly enough, you can actually watch sunspots appear and die off and go away every about 11 years or so, and they'll continue to come and go. The movement of sunspots indicates that the sun is, in fact, spinning, similarly to the planets. And so you may see, at the top here, you may see a sunspot that's right here, and then the next time you look at the sun, that same sunspot is over here. And so that indicates there's a motion here, that it used to be in one position, but it has now moved. So we assume that the entire sun is spinning on an axis. We observe these things. Okay? So again, cool things that we can learn as we study the sun. Well, if we look, you'll notice the sunspots, and these are just, all we're talking about are just little sunspots. And again, these are cooler regions, but again, 600 miles in size. They look very tiny, but much larger than you'd think. Of course, sunspots, you can see them in large regions. You can even see kind of an attraction between them, which is interesting. That's why we mentioned the magnetic field. Some even speculate maybe there's a north and south pole that's pulling magnetic particles through and making that sunspot. After that, we talk about what's called the chromosphere. The chromosphere. It says outside the photosphere is the chromosphere, the lowest layer of the sun's atmosphere. And so as we start to make our picture, okay, this is the sphere of color. And so it says the lowest layer of the sun's atmosphere. This is outside of the photosphere. So essentially what you have is you've got the sun and then just a thin layer of atmosphere. This particular layer of the atmosphere is called the chromosphere. And of course the prefix chromo means color. And so here is your photosphere. That's the part of the sun that we see. It's so bright that we actually see it over the chromosphere. And this sphere of color is what we typically see during eclipses, but I'll talk more about that. So the chromosphere is this outer atmosphere. Okay, moving on. During a solar eclipse, that appears as a bright reddish pink fringe. And so if you ever get a chance to see an eclipse, you will notice these colors. There's a little bit of the photosphere just shining out here, but you'll notice these pink regions. Okay, and these are the chromosphere in that lower part of the atmosphere that we can see. And so that might be helpful to your understanding. So we've got the chromosphere. That's 11,000 degrees Fahrenheit at the bottom and about 40,000 going up. And so in our atmosphere, on our planet, as you go up it gets cold, but as you go up on the sun it actually gets really hot, like 40,000 degrees hot. And so that would be interesting. Viewable by special filters which block the photosphere's light. So if you want to see the photosphere, you have to block, if you want to see the chromosphere, I mentioned this, the photosphere is so bright that we never see the chromosphere. Okay, if you want to see that, you must put a filter that blocks photosphere light but allows chromosphere light. And so if you have that, you might get to see the chromosphere. Again, it is this pink fringe that is visible during an eclipse. I'm getting rid of some of this ink so you can see better. This is what we're talking about. So notice we have a core. We mentioned the photosphere, which is kind of the main portion. The chromosphere is kind of a layer that's outside of that. It's kind of like the skin of an apple. Photosphere would be kind of like the flesh of the apple. Notice the photosphere is covered with granules. All right, spicules. To me, this word screams spikes. Okay, so it screams to me spikes. I erased it, spike. Okay, and that's exactly what it is. In fact, as you look, it's the flame-like column of gas which continually erupt from the chromosphere. If you were able to look at the sun, you will notice that this lasts 5 to 10 minutes. It's shaped like blades of grass, and many times we call this the burning prairie. So if you look, you'll notice kind of this haze, this fleshy haze that goes around the sun there. I mean, you can kind of look at it, it kind of looks like someone's burning some grass there. Those little things, and I say little things for a reason, they look small, but they're actually very large because this is the sun we're talking about. It's the flames. So when someone draws a picture of the sun and they draw these rays off of it, those are the spicules that they're drawing. Of course, those are part of the chromosphere, or the sphere of color. So they make that burning prairie look. All right, so the granules are the bubbles, the spicules are the spikes, or the grass. Now, another thing you might see is if you look at the sun, you might occasionally see this big arch of flame jump across the sun. Not a rainbow, but a giant arch of flame. Those particular things we will talk about in a moment. But first of all, these tremendous bursts of energy that interrupt spicules. So originally you have a spicule, which is kind of like the blade of grass, and they can burst out a lot stronger. We believe these are caused by magnetic stress. Part of that is because of the radio communications they damage. You must, of course, use special telescopes because otherwise you can't see this. And you will see these solar flares. Solar flares are just, notice the granules, the bubbles, and then you've got spicules, little spikes, all the way through here. But this giant thing is a solar flare. Okay? So that's important. Moving on, a couple more pictures here. We have the Earth to scale and the size of that. Look at how big these solar flares can get. Speaking of which, we just talked about one, but a solar prominence is a stream of dense gas erupting off of this and returning in a loop-like fashion, almost like what we just saw. That's a solar prominence. And so a loop joining the two spots travels so fast that they could go from the Earth to the Moon in 6 minutes. So a solar prominence is that arc that is formed by a solar flare. And so that's all you need to know about that. Again, the Earth is so small in comparison to the size of these solar flares. I'm looking on 326 to get some of that information. Okay, so I would definitely encourage you to look at some of the material there. The pictures on page 326. All right, so if you take the Earth, or the sun, you start on the outside layer. We call this the photosphere. Okay, from there you've got the chromosphere, so that's the low layer of the atmosphere. But it even mentions after that another region called the transition region. That's, that's from, oh, I got an eraser. That's from here out to the next layer. It's transitioning from this type of atmosphere to the next layer. And so let's talk about it. This is the very thin layer of atmosphere outside of the chromosphere. You'll notice even on page 326 that you have the chromosphere. I'm talking about that picture at the top left. You'll notice the chromosphere is pretty small. The transition region is just a little bitty layer, and it gets from 40,000 degrees to 1.8 million degrees in that region. It's transitioning in heat, it's transitioning in properties, it's huge. Now, what's important about this is the area that releases that UV radiation that our atmosphere protects us from. Now, interestingly enough, they can only study this in space because none of this radiation actually gets to our planet. Okay, so again, a pretty complicated picture, but if we look at the bottom here, we got the photosphere. That's the part of that touches the surface of the sun. Again, I say the surface of the sun. It's a gaseous star. You can't actually walk on it, but that's the photosphere. Then you have the chromosphere. That's the layer outside. Transition region, notice they just represent that by a dotted line. And then, of course, our next region we are going to call the corona. So we call this the corona. The outermost layer of the sun's atmosphere is the crown. And this gets to about 6 million degrees Fahrenheit, just massively hot. Visible to the unaided eye only during a total eclipse like the corona is. And so you can only see these different things during the eclipses. So in an ever-changing layer of the solar flares, action, and prominences, the corona is where you get to see some of this action during an eclipse. Often this is filled with increasing or decreasing holes in the atmosphere. So moving on, this is the corona. It's the crown that goes around it. I said earlier that those were the spicules. Perhaps these parts of the sun are the corona. That's maybe how people see that. But it's the crown that the king wears, and so, you know, the kingly crown. That's what I'm talking about. It looks more like a mohawk, but you can forgive me. All right, so that's the corona. Summarizing some of that, we've been talking about the core, of course, that's the inside. Then you have the photosphere. Outside of that, you have the chromosphere. That's the next layer. And there's all kinds of bubbles going on, granules, prominences, solar flares, spicules, supergranules. And then outside of that is this flurry of what we call the corona. And so you definitely want to know these terms. This is definitely going to show up on a quiz in the future. Talking about solar wind. We talked about that earlier in the year. One of the most dangerous things about the sun is it produces harmful particles. Those harmful particles that come directly from the sun towards the planet Earth, not to scale by the way, the sun's bigger, those are called solar wind. Of course, in space there is no wind, but that's what we call these charged particles that head towards the Earth. Remember, our magnetic field protects us from these. And so some of these particles get trapped in our northern areas and our southern areas, producing auroras. And so, looking at those, we've got solar wind. This is a high-speed stream of charged particles ejected from the sun, about 250 miles per second. We're talking about really, really fast stuff. I could probably go about 8 feet in a second, maybe 10 feet in a second, but not 250 miles in a second. This reaches the Earth in 4.5 days. Very, very fast. We're talking 93 million miles in 4.5 days. This blocked from the Earth by the magnetosphere, we mentioned that. It extends out of the edge of the solar system. And so the solar wind, by the way, super cool picture. But whatever it is, this is not a real picture, it's a graphic to show it. Notice this really cool solar prominence going between sunspots, solar flare right here, but the solar wind that's protected and shielded by our magnetosphere. Notice the magnetotail, and the magnetosphere is in no way a sphere. Okay, and so that's what we are talking about. All right, so at this point we have reached the end of lesson 143, and I'm going to give you an opportunity to take some notes, go back through the video, and get something from your proctor if they need you to get any extra notes. But at this time I'm going to end the lesson and allow them to give homework for you.